Okay? Now, whilst you have the paper there, let's also talk about number 2. Is that okay? Any question? Comment? All right, so number 2, we've got this this picture here. -5, we kind of got, actually, it's -3, got something that. And then at 4, we kind of got something. All right, so you got your handout there. You don't necessarily have to draw this, but what I want to mention is the limits here. Well, let's look at the limit as x approaches -3. You've probably seen graphs like this before, but from the standpoints of limits, as we approach this break up here in the graph at -3, what could we say about the limit as x approaches -3? Well, from the left, we're headed straight down, basically, and then from the right, we're headed same direction there, down. So it looks like it's going straight down, or to, what's the function value doing? Well, the function value is just getting less, smaller and smaller and smaller, more and more negative, I guess is a better way to say it. So technically, yeah, you could say it does not exist, but we can be more specific about it here in that it's negative infinity. It's negative infinity. And I don't know if I'll have time today on this lecture to do the table aspect of that, but yeah, that we could say we can go to negative infinity. The values just keep getting more and more negative. The closer and closer you get to -3 on either side, the values just keep getting more and more negative. Now on the other side, we got something going at 4 there. Well, now at 4, we are into a does not exist category there, aren't we? Because it's negative infinity on this side, positive infinity on that side. So yeah, the two don't match up, so I can't even specify there. So yeah, that would be does not exist, but I can break that into the two parts, do the limit. You see x approaches 4 from the left, and then limit as x approaches 4 from the right. I can break that one up. What would it be from the left? As I approach 4 from the left, it would be negative infinity. And then from the right, it's positive infinity. So technically the limit does not exist as you approach 4, but you can do it one-sided like that. Okay? Is everybody with me okay on that? All right. We'll come back to infinite limits and later, but a couple other quick little points about some things. First of all, there are some easy limits. And we're always looking for easy things, especially in calculus class, right? There are some easy limits. For example, if I have the limit as x approaches 2 of 3x plus 5. This is an easy limit. You see the thing about the limit, let's go back here and let me write it up here. X approaches 2, x minus 2, x squared minus 4. The thing about that one was I couldn't substitute x is 2 into that, right? Because I wouldn't get an answer. So that's kind of why I have to go in and look at x approaches 2 from the left and from the right. We've done it with the table thing. However, does such a problem exist here? I don't have a problem substituting 2 there. And so the point of this is, if I can substitute it, turns out, and get an answer, turns out the limit, that'll be your answer to your limit. I can actually substitute the 2 here, can I? And get a value. And so if you can substitute your x, whatever x value you're going to there, if you can substitute it, then that's going to give you the answer. If I do 3 times 2 plus 5, yeah, that's going to give me, what, 11? That is going to be the limit as x approaches 2 of this thing. And the reason is, think about the graph. If you do f of x equals 3x plus 5, that's going to be kind of like the last one we did on number 1. Let's see. 5, rise, run, okay, something like that. As I approach 2, this graph's coming in here from the right, from the left, and then coming in here from the right. Yeah, it's coming in right at that, whatever that function value is, you see. There's not anything funny going on there. It's just coming straight into 11 from the right and from the left. It actually hits 11 at 2. So yeah, if you can substitute a value in, then that's what you're going to do even on a limit. Okay? So what do you get here? What's the limit as x approaches negative 4, x squared plus 3x minus 1. Same thing, right? I can substitute that in. And I'll get negative 4 squared plus 3 times negative 4 plus, or minus 1. That's 16 minus 12 minus 1, so that's 3. Okay, so those are easy limits. Easy limits, ones that you can substitute in. Matter of fact, we're going to, our next technique will be getting it to this point. So, then the other point let me make here is that also, you need to be careful with tables. Okay, let me show you that example of that. Take a look at this one. Limit as x approaches 0, sine of pi over x. Let's take a look at that limit and use tables. Tables can actually, even if you get lots of values. Well, here's the thing. X approaches 0, so again I'm looking at negative 0.1, negative 0.01, negative 0.001, so forth. Right? Same old, same old. But let's see what we get. Sine of pi over x. Okay. Again, notice this one's not one where we can substitute, so we're going to try to look at a table. And, okay, at negative 0.1, I get 0. Negative 0.01, I get 0. Negative 0.001, I get 0. And guess what I get on this side, too? Same thing. However, the limit of sine of pi over x as x approaches does not equal 0. And you can see that a little more clearly, I think. Let's look at the graph. Yeah, you might have to zoom in a little bit at 0. If you zoom in on that graph, sine of pi over x, oops. Okay? Here's the thing. This thing is just oscillating pretty wickedly at near 0. It just keeps bouncing. I think it's +1 and -1. Yeah, there's no limit in this part right here. That thing is just bouncing between -1 and +1, and it's, even though these values clearly hit 0, the next value over, if you will, does it. You know, it's going from -1 to 0 to +1. You know, about as fast as you can count it. Okay, so be careful using a table. Sometimes it can be a bit deceiving. Now, that one's kind of a special deal, but the point is, you know, be careful with what the table is showing you. Even though, if you just look exclusively at the table, I guess what we're pointing out here, we would be incorrect in that case. But for a lot of these, the table is going to be plenty of evidence, and you know, they'll clearly be going 0.25 or 0.333, whatever. So, but just wanted to make a note of that. All right. Yeah, let's go back to infinite limits for just a second. And this one, first one here, is the limit as x approaches 0 of 1 over x squared. I've already given the hint there that this is back to infinite limits, but we can definitely verify this out by a table here. Again, approaching 0. And so let's look at -0.1, done several times now, and then the positive counterparts, 0.01, 0.001. Okay, at -0.1, I've got 100 is the function value. At -0.001, I've got 10,000. And then the calculator, my calculator is showing 1e6. What do you think that means? Exponential notation? 1 times 10 to the 6th, which is 1 followed by 6 zeros. Okay? 100,000. And it shows it if I arrow over to it, but okay. All right. So on the other side, the 0.1, 0.01, same thing. 100, 10,000, 100,000. Okay? So what's happening as x goes to 0 for this function? Well, these values are just getting larger and larger and larger and larger. These are also getting larger and larger and larger. And it doesn't seem like there's going to be any limit to it, right? So what are you going to say for the limit there, you think? Positive infinity. So this is what an infinite limit looks like on a table. The values here are just going to get larger and larger and larger as you get closer and closer and closer to your x value, whatever it is. They're just going to keep getting larger. Now, of course, well, let's look at this one. What about the limit as x approaches 2, -3 over x minus 2 squared? With a table, here's what we get. So we're approaching 2, so that's going to be the low side would be 1.9, 0.99, 1.999. And this would be, high side would be 2.1, 2.01, 2.001, more if you want. Here's what we get though. Okay, so we got negative 3 divided by, parentheses, x minus 2 squared. Okay, so at 1.9, 1.99, and 1.999. Okay, negative 300, negative 3,000, and negative 300,000. And on the other side, 2.1, you get the same thing. So what you got there? Negative infinity. Yep. That one has there negative infinity. Okay? The graph, okay. Either one of them? Yeah, we didn't look at the graph, but on this one, it was this. It's like that number 2 we had. Yeah, it's going up. And this one, as you approach 2, yeah, you're headed downwards. Like, I don't know that that's exactly what, well, I can tell you what that one looks like. Yeah, pretty close. Yeah, at 2, the graphs are headed downwards. Mm-hmm. All right. Now, of course, if you look at the limit, x approaches 2 of x plus 3 over x minus 2. Well, what we see on that one is a little different story. Get the tables up here. First of all, 2.1 on this side. X plus 3, parentheses. Okay, so yeah, we see this is negative 49, negative 40, 99, negative 49, 99. 2.1 though, we get 51, 501, and 5001. So what's the story there? Limit as x approaches 2 does what? Doesn't exist, because these are going to negative infinity, these are going to positive infinity. The two don't match. They have to go both the same place. So yeah, this limit does not exist. However, what can we do? We can say the limit as x approaches 2 from the left of f of x is negative infinity, and the limit of this f of x from the 2 from the right is positive infinity. So we can break it up into the 2, but the limit just as x approaches 2 does not exist. Is that okay? Question on that? The other thing real quick here, if you have these infinite limits, one side or both sides going to infinity or negative infinity, the term that we use this in college algebra, the term that we use at 2 or at 0 on the other one is asymptote, a vertical asymptote. If you have an infinite limit, either one-sided or two-sided, whichever, at that particular x value, you have what's called a vertical asymptote. And they may ask you about those in the homework there, but yeah, you have these, if you have an infinite limit, one-sided or whatever it is. There is a vertical asymptote. Let's see. Whenever you have an infinite limit at x equals a, you can have a vertical asymptote also of x equals a. That's the way we'll say it. Okay, so in other words, up here, the vertical asymptote would be x equals 2. Both of these, matter of fact. Both of these have vertical asymptote x equals 2. The other one, the first one we did, x equals 0 is a vertical asymptote. The one on the handout, let's see, it looked, we had 2 vertical asymptotes, I think. You had a vertical asymptote, and you can draw it in as a dotted line if you want to. You had a vertical asymptote at -3, and then we also had a vertical asymptote at 4. Okay? So, anyway, if it asks for the vertical asymptotes, it's just wanting those where the x values of the infinite limits are. Okay?